Welcome back to the final class on statistical mechanics. This will be a summary lecture where we would like to take the student to the subjects covered in this rather long course on statistical mechanics. So, in this last summary lecture, I would like to remind the students the basic objectives of the course and certain important points. If you look back, we started by pointing out the scope of statistical mechanics. There's a lecture called Why Study Statistical Mechanics, where I tried to point out the huge scope of the subject in physics, chemistry, biology, and also material science. Particularly in chemistry and biology, it's extremely important. It is becoming important in material science also, in the synthesis of new materials. We then discussed, after the preliminaries, we tried to get going and to formulate the subject, and I pointed out that there are actually two theoretical subjects, two major theoretical disciplines in our entire arsenal. One is quantum mechanics and there is statistical mechanics. Both use substantial amount of mathematics and based on physics of like Newton's laws of motion and Schrodinger equation, many things. So quantum mechanics provides you about the microscopic world, about the energy levels, about the wave function, and very intimately connected to spectroscopy. On the other hand, statistical mechanics deals with many body, the phenomena, the properties that appear because of interactions of many molecules, like a glass of water. The properties of glass of water is not property of one individual water molecules. It is a sum total of properties. One water molecule doesn't have the solvation properties, doesn't have its flow or many other things that we know and we associate with water. So the key word is that interaction among these water molecules. It's not just water. We can have ethanol, we can have dimethyl sulfoxide, we can have argon, many of metals, liquid metals. So there's a huge number of these systems all around us, including our body, where the uniqueness of each system and the properties comes not from the constituents, but also from the interaction among them. Interactions in turn determined by the nature, of course, of the molecules and atoms. Given the interaction potential, the duty or responsibility of statistical mechanics is to explain the properties. How then water acquires its wonderful properties, why it boils at 100 degrees centigrade, why it freezes into ice at 0 degrees centigrade, why water and ethanol form such a wonderful mixture, many such things, just innumerable things that around us, which statistical mechanics set out to explain. In this huge work, one goes to develop a substantial formalism, which we discussed. We showed that how, set with this huge task, our forefathers like Mulchman and Gibbs, they formulated two postulates, postulate 1 and postulate 2. One is equilibrium probability, and the other is the ensemble average. Before that came the introduction of the concept of ensembles which I discussed at great length. That is billions and billions of mental replica of your original system so that we can talk of a probability distribution. But that works only when you assume that each system is in a different microscopic state which are equally likely. So it's equilibrium probability. And however, the averages that we in real world, the time average is much of the time. So time average equal to ensemble average, and that postulate is the second postulate. I also discussed how these two postulates need to be connected by hypothesis. That's got the algorithm. So armed with these two postulates and one hypothesis, statistical mechanics sets out to explain the vast number of observed phenomena. It's amazing that how such simple postulates and fairly innocuous postulates can lead you to explain why water freezes at 0 degrees centigrade at ambient pressure. So in this that this one first start with the ensembles. We discussed the concept of ensembles and that everything starts with the microcanonical ensemble, which is called NVE. Then there are four ensembles we discussed from microcanonical into canonical, canonical into grand canonical, and then isothermal isobaric ensemble. Microcanonical is NVE, canonical NVT, grand canonical is fugacity, volume, temperature, and isothermal isobaric ensemble is NPT. So these, as you clearly see, these different ensembles serve different purposes because often our experimental systems are different conditions. It is almost never in NVE because we cannot control the energy because our systems are always in interacting with surrounding. We do not cannot fully control the volume, though it's little more than energy, and number also. Many times molecules are getting exchanged with surrounding media like a glass of water exchanging with the paper. So we did need the different ensembles to treat different experimental conditions. Also, there is a very fundamental theoretical reason that doing calculations or theory in microcanonical ensemble is rather difficult. So then we set out with these four different ensembles. We set out to calculate thermodynamic properties like entropy, specific heat, free energy, average internal energy, radial distribution function, many other properties. But all of them go through one route, that is the partition function. The partition function is essentially weight of that particular state of the system. Like particular state is given by say NVE. Then partition function give me what is the weight of that. And that weight has to be extremized, maximized much of the time. Logarithm of the partition function defines what is called the thermodynamic potential. We discussed in great detail, like logarithmic of the canonical partition function is the free energy. Logarithm of the microcanonical partition function is the entropy. And this is then is the first step towards describing thermodynamics from statistical mechanics, which is one of the major goals. We then went after formulation of the expression for the partition function. We did several wonderful calculations. We calculated entropy, Sackur-Tetrode equation for entropy. We did the diatomic gas and vibrational rotational entropy. These are for ideal gas, where molecules don't interact with each other, but just there are many of them together. Even in non-interacting, there's some wonderful properties like the Sackur-Tetrode equation, vibrational rotational entropy, which can actually be experimentally verified in many cases, not in a completely, but 90% or so. In dilute gas, for example, is a good model of the ideal gas. Certain approximations. Then we did interacting systems. We did Ising model, which is a system of spins, and we did the Mayer's theory of condensation. And from Mayer's theory, which is a wonderful and fairly sophisticated theory to tell you how, in the presence of intermolecular interaction, you go around this calculating the partition function, calculating the pressure and the equation of state, and ultimately we show how from Mayer's theory you get the well-known virial series, which was derived long ago. The virial theories was in 19th century, mid 19th century. First virial, second virial coefficient, third virial coefficient, all those things were done and measured long time ago. But now Mayer's theory, when it was done, I discussed that the expression of second virial coefficient and third virial coefficient in terms of intermolecular potential allows us now to use the experimental result to construct the intermolecular potential. And this is actually some kind of a fitting to experimental data, but at the end you find a very important quantity, which is not just which was introduced from imagination that two molecules interact, but we had no way to know what is the interaction potential between them. But this Mayer's theory and the expression for virial coefficients allowed us to map and get the intermolecular potential. There is a big game now which is called the force field. So this virial coefficient, first time, for example, that two argon atoms interact through something like Lennard-Jones potential, that came out, and the parameters of the Lennard-Jones potential came out from this theoretical expression derived by Mayer for the virial coefficients. So wonderful, really wonderful stuff. Continuing that, we spend a lot of time on phase transition because that's an important subject in chemistry, and to understand how different solid phases form, how condensation takes place. So Mayer's theory told us how intermolecular interactions to be included. But that's a very difficult theory, which was further developed later through clusters and other things. But there is a simpler and more direct approach to understand many aspects of phase transition, the universality of phase transition, without going through intermolecular potential. That's called Landau's theory of phase transition. So we discussed quite a bit of time of Landau theory, which is the free energy expansion. Free energy expansion in terms of the order parameter. We introduced the concept of order parameter. Free energy as a function of order parameter, different phases have different free energy, and what is the basic structure of. So then after we studied the phase transition or thermodynamics of phase transition, like the discontinuity at the phase transition, we discussed first order phase transition, we discussed second order phase transition, that is called Ehrenfest phase classification, and how Landau's theory kind of unifies these different things into a beautiful scheme based on free energy. We then subsequently studied kinetics of phase transition. We studied nucleation and spinel decomposition. These are wonderful subjects, and they are very useful, because nucleation is something which is, you see raindrops falling, ice forming all around us, or now that the ice melting. So nucleation is a very important thing. Spinel decomposition, on the other hand, is a theory of pattern formation, how beautiful patterns form in nature, and this is also a kinetics of phase transition, a part of kinetics of phase transition. Then we went on and we studied binary mixtures. Binary mixtures is a wonderful subject where we studied in undergraduate physical chemistry in great detail, and also biophysical chemistry, that how binary mixtures, two liquids A and B mixed, they acquire new properties, and that property is extremely useful in the chemical industry and also in biology. So one needed to understand in terms of intermolecular interactions how these unique properties and the composition dependent of the properties of a binary mixture, how much A and how much B we mix to get this property. That also is a prescription given by statistical mechanics, and a lot of work has been done along that line, and we discussed that. Then we went into describe the 3 lectures we found on theory of liquids, radial distribution functions, and the extremely important function called GR, which describes many properties of the liquid. Then we covered in detail again 3 lectures on polymer solutions, polymer thermodynamics, Florey's theory, sol-gel transition. We discussed the Florey-Huggins theory. We discussed how polymer collapse takes place. We discussed why polymers in solution good solvents are swollen, and so the effective interaction between monomers propagated through the solvent molecules. We discussed polymer in great detail. Finally, in 2 lectures, we discussed computer simulations, which is extremely important because you could not do computer many of the complex interactions. We cannot do statistical mechanics, and these are very important subjects that we dealt with the so many different. Uh, we went through huge number of subjects, and we did quite a bit of theory, quite a bit of mathematics, and however, as I was saying, when in real molecules, they are, as I mentioned in the lecture, the interactions are quite complex, so we cannot do them through analytical work. Even Mayer's theory, you found how difficult it is to push through Mayer's theory. So the field was suffering, but at the same time, in 1960s, the computers came in, and the statistical mechanics again could go ahead because they could now treat those complex interactions using the principles of statistical mechanics by computer simulations, molecular dynamics, and Monte Carlo simulation. They are all based on principles of statistical mechanics. That one should not forget that. But so computer simulation, doing the people doing those kind of computer simulations are actually doing statistical mechanics. But instead of doing it analytically, pen and paper and pen and pencil, they are doing it with